Hi, good morning everyone. Thank you for welcoming us today. Today we are going to see how the JavaScript engine actually is and what is it about. So first of all, I'm just wanted to look at the raise of hands who all have heard of JavaScript engines before. Okay, two, three, four. Yeah, so quite less. So that would be interesting because most of the people are quite unfamiliar with this. And thanks Julia for the shout out in your previous talk. It was a very interesting one. So starting off with the JavaScript engines, let's first talk about why they are even important to us and why should we as a JavaScript developers know about it. So firstly, it is really helpful in distinguishing other technologies like WebAssembly, which is also a very recent one, like only from this past decade. It basically the main reason for it is to understand how our high-level code that we are writing in JavaScript gets converted down to the machine code that actually runs on the machine. And finally, it also helps us to write optimized code as a developer. It is not just a theoretical concept. We are going to get some key takeaways that will also help us to write more optimized code in our day-to-day coding practice. So yeah, let's dive right in. We are going to just quickly do a recap of JavaScript and its runtime environment in 5 minutes so that everyone's on the same level, and then we are going to take it up from there. So the JavaScript language has been the language of the web for the last around 30 years. It started as a document sharing platform and now it is used to build all sorts of apps and websites. The key points about JavaScript is it is synchronous and single threaded. Every line is executed one at a time and there is no multi-threading. Next is it is untyped or dynamic language and all the variables and the objects are assigned the types at the runtime. And finally, it also offers functional programming. It is a multi-paradigm language and the functions here are first-class citizens, which essentially means that they could be returned from another function or either they could be passed through as an argument to a previous function or something of that sort. So everything in JavaScript happens in a execution context. The firstly, as soon as your program loads, a global execution context is created, and from further on with each function call, a new execution context is created, which has basically two parts. One is the memory creation phase, and second is the code execution phase. And there are two main components: a memory component and a code component. Memory component essentially consists of your variables and objects which are initially assigned none of the values, they are undefined, while your code component has all the lines of your code. And on the runtime, while going through the code component, the engine or the compiler assigns the types to these memory component variables and objects as per the type feedback and whatever you have assigned in your code base. So coming to the JavaScript runtime environment, it looks something like this. These are all the main environment, all the main components with JavaScript engine at its heart, which essentially consists of a heap and a call stack. Besides that, we have your basic JavaScript file that everyone has written on. And then you have your console to look into errors or anything of that sort. Besides that, there are web APIs like geolocation, fetch API, Bluetooth API that we must have used somewhere or the other. And then there are two main queues, a microtask queue and a callback queue. A callback queue gets all the callback functions that you get from your call stack, which have been included as a part of the execution context. And your microtask queue is kind of a higher priority callback queue, wherein the callback functions from APIs like fetch, which have a higher priority, are included, and they are the first ones that are included in the call stack as soon as it gets empty. And then coming to the call stack and memory heap, the memory heap is basically for dynamic memory allocation. The call stack is simply a stack with a LIFO principle for taking care of all the execution context and the callback calls. And then there is also garbage collector, which we will also be looking, and how basically the engine takes care of all the garbage collection in your engine. So coming to the specific browser engines which are pretty common, the V8 by Chrome. It is also used by node.js, Dino and other Chromium browsers. Then again there is a SpiderMonkey which is used by Mozilla Firefox under the hood. And then these are all other three browsers, three engines. but they have also recently shifted to V8. So I would be talking more specifically to V8, but in general all the JavaScript engines are kind of same and most of the functionalities are overlapping. So basically a JavaScript engine at a very higher level does something like this. It takes in your source code and converts it to the machine code through a series of steps, and the main ones are parsing, the AST, which is a creation of an abstract syntax tree, and then there is interpretation and compilation. So we'll be talking about them in a kind of great detail, but there would be still a lot of things that you could go home and explore. So a basic diagram of V8 engine, which is presently in function, is something of this sort. Your JavaScript source code is taken by the parser, which is eventually converted to an abstract syntax tree, and from there on there are two parts. One is the ignition interpreter, and then second is your turbofan, which is an optimizing compiler, and at the end you get your optimized code, which is used by your code base or by the engine to run the code on the web. So we will be talking about them later on, but first, before that, since JavaScript has been here for long and most of us have been dropped in that timeline with no sort of a previous history, so I would like to take you a little bit through the history of how the engine has evolved and why it evolved in that particular way. So in 2008, the compiler pipeline started off with a simple structure like this. We just had one semi-optimized compiler which was called CodeGen, and it was used to emit out a semi-optimized code. So it was not that fast as it is now. So there were optimizations along the way. In 2010, there was two parts that were created. One was a simple baseline compiler and the other was a optimizing compiler. Optimizing compiler specifically means that it takes in your type feedback from the compile time, that what type is being assigned to all the variables and objects, and also takes in consideration other aspects like the machine on which your code is running on, and using all those things, it emits out an optimized code which is way faster than the initial source code that you have written. In 2014, there were different pipelines created, which had two optimizing compilers. It was similar, but it was kind of getting more complex, both on the maintainer side as well as on the execution side in the engine. And then finally, in 2016, it could have not been worse, as it had three different pipelines, and it was very difficult to maintain that which one should be used in what scenarios. So finally, the Google team decided to come up to this final conclusion and keep it what it is now. So before diving individually to all this, let's talk a little bit about WebAssembly and how this JavaScript engine thing applies to that. So WebAssembly is a very recent thing, and it is a portable binary code format. So it allows you to run code written in different languages other than JavaScript, and they are actually made to run on the web. So it is basically there to complement the JavaScript and not replace it. So it is a portable binary code format. Your code written in other languages is compiled to a WASM module, WASM.wasm file, and then it is eventually run through a different pipeline which is present inside the JavaScript engine in all the browsers. So that's how your WebAssembly code is run on the web. Now talking about how the JavaScript engine and the optimization applies to WebAssembly. So let's see this simple WebAssembly pipeline. I hope it is visible till the end. So initially, if a particular function in your WASM module is called for once, the liftoff compiler, which is the baseline compiler of the WebAssembly pipeline, executes that function, and if that same function is executed twice, then it is considered a hot function. Hot function means a function that is being called again and again by your code, and hence your turbofan, which is an optimizing compiler, takes the charge and basically optimizes that particular function so that the next time your same function is called by your source code, it does not take the whole process of executing that, and it is faster by using that already generated optimized code. So hence, after this call, your turbofan omits out optimized code, and hence after this, whenever your same function is called, your optimized code is directly used, and you don't take that long for that particular function to execute. So in that way, you are getting faster speeds. So that's the basic concept of optimizing that is happening both on the JavaScript pipeline as well as on the WebAssembly pipeline in every browser. So now diving into all the different stages of the JavaScript engine, starting with the parsing. It is basically taking in your source code and removing all the unnecessary parts of it, like semicolons and all the assignment variables which are not actually needed by the engine. And then finally there is second part of your parsing stage, which is called the parser, that takes in that final list of tokens and creates an abstract syntax tree. It is like a simple generic tree that we have seen in data structures, and your whole function block is divided into different parts with all the variable declarations, all the values, as well as the return statement. So just to get a better view, there is this cool website that allows you to write a code and see how the abstract syntax tree is created. So I will want you all to have a look at it. So this is the website, and this is the particular code that I have written. Just a moment. So this is a simple var const variable that is assigned a value 5, and a function is returning the thrice of that particular number. Coming to the right side, you could see this tree section which has this body part wherein you have two different things. One is the variable declaration and the other is the function declaration. So it has basically tried to divide your function into different blocks, so it is easier for the later stages of the compilation. So coming to the variable declaration, you can see that it has started at the 0th index and moved towards the right at 14th. So for example, you have started with C, the const first letter C, and it ends at 5. So these are 14 letters including the spaces. So that's for the sake of simplicity. And then the kind you see here, it is the const kind for that particular variable. And in that particular function, you could see all types of different things. Your block statement, your return statement, and then the argument is a binary expression since we are returning thrice of that particular number. So you can explore this if you wish to dive deeper. Continuing with our presentation. Next up, there is a simple concept of just-in-time compilation that is being used for this whole process by the engine. So you have ahead-of-time compilation languages like C++, Java, since they are statically typed and they have the types for all the variables and objects pre-written. Now there are also interpreted languages like JavaScript itself, which are dynamic and don't have the type already explained. So just-in-time compilation is a combination of both, since in the first phase at the compile time or the baseline compiler takes in all the type feedback by quickly running your code, so that you could use that type feedback to basically optimize your code by the optimizing compiler. So it is kind of using both of the things, and it is known as just-in-time compilation. So coming to the first of the main parts, which is an ignition interpreter. So the first is ignition interpreter and next is the turbofan compiler. So interpreter is used because we need to convert our source code into a mid-level code which is called a bytecode. So if you are familiar with Java, there is a bytecode as well, which is kind of a universal format which could be imported to different sort of machine architectures, and it can run in either of them. So similar kind of concept is here. Bytecode is a sort of, you can say, mid-level or assembly level language which is specific to your machine architecture. So it is way faster than your original source code. But why do we actually need it? These are the three main things: because the memory usage is reduced, because your unnecessary things are removed completely. Then you have your faster times, because it is kind of on the lower level side and not exactly high level that it was earlier. And then already the pipeline complexity is reduced. How it is reduced is shown in this particular thing, because it is now the source of truth for your optimization and de-optimization. Now your bytecode is used to optimize your initial code to the final code by using the type feedback that is being collected on the compile time. But in case your type for a particular object or variable changes, since it is JavaScript, we can anyways do that in any part of our code. Your whole function is de-optimized and it is brought back to the original bytecode that was initially generated. So that process is done once again, and every time whenever your type is changed within any part of your code. Now the another great thing with which your memory usage is reduced is you don't need to keep your original JavaScript source code into your um, into your engine, because that is no longer needed, as every time you optimize or de-optimize, it just needs to be at that bytecode stage, and everything before that can be get written off. So memory is greatly reduced. So just to see how bytecodes are looking like. So if you have any time have had a chance to work with assembly language or learn about microprocessors, so there is a register thing going on there with an accumulation register that is used to load memory into your registers in a microprocessor. So these are the kind of instructions that go on there. So for example, if you see the first one, LDA 0, it means load 0 value into the accumulator. So all of these codes have some sort of meaning, and your bytecode is basically using only these along with values to generate whole of your source code into that binary code format. Going next, this is a simple illustration of how your initial one-line high-level code could look like in the machine code format through the bytecode stage. Now coming to the turbofan stage, which is the optimizing compiler. So as we already talked about, it takes that original bytecode, generates a type feedback by quickly running the code, and then uses that to generate an optimized piece of code, which is way faster to access whenever that function is called again during the code base. And for de-optimization, everything is thrown away and we are going back to the bytecode stage again. Now to understand the whole optimization thing and how you can write greatly optimized code is through this key concept of hidden classes and inline catching. So hidden class is a concept wherein a different class is created for every different possibility of how a function could be initiated. So for example, whenever you create a user function, a class is already created behind the scenes. So whenever a similar function with all the similar arguments is declared, that hidden class is accessed by the engine. So every time you add a different property, for example name, phone and address, these are all different hidden classes with all these different properties. So if a user object is created with two properties, name and phone, the hidden class 2 would be used for the access purpose, and hidden class 3 would be redundant in that case. So why is this done? Because for example, you have this stage when you have created the name property for that particular object. The hidden class 1 could be easily accessed within the memory, and that could be used for the optimization and de-optimization purpose. And inline catching is another main concept, which is caching the already accessed hidden class. So in case that similar hidden class needs to be accessed again, that could be done way faster than it took at the earlier time. So this is highly useful, and we will see that in a bit. But before that, let's quickly go through the garbage collection and how that is happening. So garbage collection has been done in two major methods. One is the mark and sweep algorithm, and one is your semi-space collection. But JavaScript uses both of these, and how that we will see. But first of all, mark and sweep algorithm is a very famous and traditional one. But for this particular algorithm, the thing you need to know is that the program needs to be stopped for a while in order to perform this garbage collection. While in the semi-space collection, it is faster, but it is not very accurate as in comparison to mark and sweep. So a combination of both of these is employed in order to keep an accurate as well as a faster garbage collection. So how that is done is displayed through this image. Your garbage collection is done in two generations. One is the young and one is the old one. So whenever the first time your garbage collection is done, it is done through that semi-space collection technique in the young generation. Your object is passed to that first stage, which is called the nursery stage, and if it survives that garbage collection, it goes on to the intermediate one, and if it again survives that garbage collection, it is finally moved on to the old generation. But before going to the old one, how is this garbage collection happening in the younger one? Your entire memory heap is divided into two parts, a from space and a to space, and the recursive transfer of the functions of all the values is being done and you are marking all the objects while going through them if they are still actively used in the code base or not. If they are not being used, they are not marked, and eventually they are get written off and they don't basically survive that particular collection, garbage collection. So after these two processes, if all the things that survive the garbage collection are moved to the older generation, so what happens here is it is done in quite a bit more of a time stage. So it is not done as frequently as the younger one, but it is more accurate. And since these things were definitely being used earlier, so they need to be looked upon at a more gap time than the newer ones. And if they don't survive this, they are getting rid of. And if they are survived, they are still stored in the older generation. And mark and sweep is applied here because the program is being paused for that particular thing. Now coming to the last stage of the talk, which is how we can write optimized JavaScript using all these things that we talked about and this knowledge that we gathered. The first key takeaway is that you should declare your object properties in a constructor, because for every property you declare, we saw that a new hidden class is being created. So whenever you add upon any property later on in the code, a new hidden class is created, which particularly means that the code for that particular case is being de-optimized and later on optimized again. So that is basically using more of your time, and it is reducing the performance of your code. Next one is a quite important one, which means that the function argument types must be fixed. So for example, since JavaScript is a dynamic language, this is a simple function which could return sum of two things, which could be of any type, which is we call in a technical term shapes. So you could return either numbers, letters, or Boolean values, anything. So if you use the similar function for all these different calls, these are all the terms given to them. So once you get past the fourth stage, using that same function for 4 different calls with different shapes, that function is permanently de-optimized. So every time this add function is being used after that 4 stages, your compiler always goes through the entire process of optimization and from the bytecode to the optimized code stage. So that basically reduces your performance of your code drastically. So that needs to be taken care of. And the last two good bits will be the for in loop for the iteration. So for the iteration in JavaScript, you could use various ways like the keys method on the object or the for loops. But the for in loop has been seen to be almost 3 times more performant than all the other ones. So for most of the cases, I would suggest that you go on with for in loop. And the last thing is keep object property ordering constant. So if you try to play around with your properties order, for example, the hidden class we saw that had name, phone and address. If you try to declare the name, address, phone, so it essentially is creating a different hidden class, which is hindering your performance once again, as per the optimization way we saw. So yeah, that would be it from my side. If you have any questions, I am here and I'm open to talk about it. Thank you.
Thank you for this information. So you talk about whole web internals. That's so great. So you talk about garbage collections, just-in-time compilers, parsers, and so on. So that's so great. Yeah, so praise and action.